Hello, my name is David Schleitz from the University of Wisconsin-Madison, and today in this video I will be summarizing the work in our paper, Modeling Architectural Support for Tightly Coupled Accelerators. So, as a summary of what I'll be describing in this video, we talk about how fine-grained accelerators are becoming increasingly common, and this is emerging tightly coupled accelerators, or what we call TCAs. So TCAs present a complex interaction between the architecture and the accelerator design. And so we create and validate a new analytical model in order to estimate the performance differences of different TCA implementations. And we determine TCA design decisions for various architectures. This model also helps us reason through the complex design space for TCAs in their implementation. And the model gives some takeaways, such as saying that high-performance cores should have nearly full out-of-order execution of their TCAs. And the more fine-grained the accelerator is, the more out-of-order is required for the TCA in order to maintain sufficient acceleration. And we also show that each level of out-of-order execution has a different optimal utilization between the TCA and the core itself. So we define an accelerator to be any circuit that's performing a function, algorithm, or group of instructions in order to reduce the inefficiencies of the general purpose core. And these inefficiencies can either be for performance or for energy purposes. And these accelerators are becoming increasingly common for many different reasons. One of them can be for dark silicon, in that there might be more silicon that can be in the system than can be powered on at a given time. So we can afford to have an accelerator in order to not be powered on all the time, but when it can be used, can maintain these benefits of acceleration. And with the slowdown of Dennard scaling in Moore's law, as architects we are pushed in order to maintain performance improvements while not violating power budgets. And so to kind of give an example of how different functional units have evolved as a form of acceleration, if you look at floating point execution, it originally was done through emulation and software. And so a floating point operation would take dozens of cycles in software, but as these sorts of execution became more and more common, it became worthwhile to move these software functions into hardware units. So we created floating point units and floating point registers in order to reduce the inefficiencies of software. And to give a more recent example, is we look at NVIDIA in their Volta architecture. They now have instructions and designated hardware units in their tensor cores in order to do matrix-matrix multiplication in floating point operations. And so on the flip side, from the other side of accelerators that are being designed, there's been more and more proposals that have been discussing these very fine-grained accelerations. So there's been work that shows that for certain workloads, in order to gain speed up, the only way that you can get the speed up is by accelerating these frequently invoked very small functions. So these functions might involve some sort of heap management, doing string manipulation, or hash map operations such as gets and sets. And these are on the order of tens to hundreds of cycles in execution, but they're invoked frequently enough that if you accelerate them, you can get significant speed up in your workload. And when we look at the existing models for accelerators such as LogCA or the Gables roofline model, they show that when you have these fixed cost overheads or latencies, that although they're constant values, when you're talking about these fine-grained accelerations, that these constants can end up being a significant portion of the overall execution time, and you can start to really diminish the expected gains from your accelerator itself. And so when you traditionally think of accelerators, it might be that these loosely coupled accelerators might use some shared memory or a shared bus, and it can be thought of as some sort of external device. But in order to think about these tightly coupled accelerators, we're talking about moving these accelerators tightly coupled into the core and acting as another functional unit. So by having another functional unit, you're now thinking in a different realm of having things such as other functional units have, like in-order commit, having designated instructions in order to invoke these accelerators, as well as doing data passing through the register file or coherent cache hierarchy instead of through the shared bus. And so there's a lot of unsolved questions when you're building these tightly coupled accelerators, such as, am I going to allow concurrent execution of multiple tightly coupled accelerators? Am I going to allow these accelerators to speculatively execute? What happens on misspeculation, and how do they recover? And these are all sorts of questions that are yet to be fully explored. And so loosely coupled accelerators are typically invoked non-speculative as a way to only invoke it once it's known that the execution is supposed to occur. And similarly, a tightly coupled accelerator can be non-speculative by draining the reorder buffer before beginning execution. And loosely coupled accelerators are often coarse-grained enough that the CPU can context switch during the execution and resume through interrupts or polling mechanisms to delay younger instructions from execution. And these mechanisms are impractical for tightly coupled accelerators because they only are executing on the order of tens of cycles. So the analogous for TCAs is having a dispatch barrier in the front end of the machine so that younger instructions are not allowed to enter the machine until the tightly coupled accelerator finishes. And so the advantages of having the reorder buffer drain is eliminating the need for recovery hardware, since the TCA is non-speculative and it won't have to undo for misspeculation because it will never misspeculate. And the advantage of having a dispatch barrier is the elimination of the tightly coupled accelerator rename logic in checking dependencies between the TCA and younger instructions. However, the disadvantage to having these mechanisms is the reduction in concurrency between the core and the TCA. And so by either implementing or not implementing these barriers, there's 4 different implementations that are possible, all with differing hardware costs and performance. And so we denote these 4 modes by saying whether or not they allow concurrency of leading or trailing instructions. So the leading concurrency comes through speculation, and the trailing concurrency has by not having a barrier so that younger instructions can execute while the TCA is being invoked. And so first we want to look at, well, what is the performance difference of these 4 different modes? So here through simulation we show 2 different accelerators, one with a speed up of 2 and one with a speed up factor of 10. And in the fully out of order mode, we can get the full levels of speed up that we would be expecting from these sorts of accelerators. And so again, this is the one without the reorder buffer drain and without a dispatch barrier. And however, when we operate in the other 3 modes that have some level of either the drain or the dispatch barrier, there are overheads that can change the overall speed up of the program significantly based on the implementation. So in here we're showing for different levels of percentage of code that's acceleratable, the levels for speed up of these same accelerators but operating in these different modes can be very different. And so what we hope to do is create an analytical model in order to estimate the differences in execution times so that you don't have to go through this process of going through a full detailed simulation in order to get the answer of what is the expected speed up in these 4 different modes. So in our analytical model, we break up and we have these 7 different parameters, and we break them up into, on the top, purely software parameters such as the percentage of instructions that the TCA can accelerate and how frequently you're invoking that TCA. And then on the bottom we have purely hardware parameters such as the size of the reorder buffer, the width of the machine, and the time it takes to commit instructions in the back end. And then in the middle we have some software and hardware parameters, but again the only values that are needed, these are easily obtainable by just running the execution, and you can see what the average IPC for that program is. And as you're designing an accelerator, you have to know what is the speed up factor of the accelerator itself versus the software implementation. And so the way our analytical model works is basically we do interval analysis of looking at the average case of accelerator versus non-accelerator instructions. and we make a few assumptions. So again, we're looking at the front end of the machine, and we're saying that non-speculative accelerator instructions can begin immediately once it enters a pipeline. And we also assume that the IPC of the core is constant during this interval analysis when it's not stalled. So in the first of these four models that we'll look at is the fully out of order case, where there's both leading and trailing concurrency by not having a reorder buffer drain and not having a dispatch barrier. So in this case, you have non-acceleratable instructions that are being executed on the core and acceleratable instructions that are being executed on the TCA. And you can get full concurrency between these two because you have no reorder buffer drain and no dispatch barrier. And so the only other case that you don't get full concurrency is if the accelerator takes too long to execute. It could be where the reorder buffer fills up and the CPU has to stall until the accelerator commits. And so with each of these formulas, we are designating the amount of time it takes for the acceleratable, non-acceleratable, and stall penalties to occur. And the overall execution time is just the maximum of the non-acceleratable code in the CPU plus any stalls the CPU might occur, or the time for the accelerator itself to do execution. So I'd encourage you to pause the video to be able to understand these formulas or to read our paper for more details. And the main thing to note is, again, we're just using the 7 parameters, and each of these are simple arithmetic operations as well as a few min and max functions. So now by looking at the second mode, this is the case in which instead of full out of order execution, there is going to be a dispatch barrier which prevents trailing instructions from having concurrency. So in this case, there are non-acceleratable pieces of code that are being dispatched through the typical core, and then as soon as the TCA instruction is invoked, then there's going to be a stall in the CPU until the accelerator both executes and commits. And so the overall execution time can be based on the time it takes for these instructions to go through the CPU, as well as the time it takes for the TCA to execute and commit. So in the third case now, we're looking at where there is no leading concurrency, so the TCA is non-speculative. So for here, as soon as the accelerator code would normally be dispatched, there's going to be some drain penalty of waiting for the reorder buffer to drain before the accelerator begins execution. So this creates some latency within the accelerator execution time that must be now modeled into this max function to say what is the overall execution time. And similar to the full out of order case, by having this extra latency, there might be a time now where the reorder buffer is now going to be full, waiting for the accelerator to finish. And so through each of these, our formulas are denoting what each of these potential penalties may occur and the overall execution time. And then in the last of the 4 modes, we have the non-leading and non-trailing concurrency, and this is the case where you have both the reorder buffer drain to be non-speculative as well as having a barrier in order to prevent future instructions from beginning execution. So here you have the penalties of both, in which the instructions that are going into the machine, now there's going to be some delay while the reorder buffer drains before the accelerator can begin its execution, and at the same time the core is not able to dispatch any new instructions until the accelerator finishes its execution. And so in our paper, we have more details on how we validate this model, but basically we look over 3 different workloads in the existing heap management proposals, as well as dense matrix multiplication, as well as a adaptive micro-benchmark in order to test over various different scenarios. And I would encourage you to look in the paper for more details on our validation of our model. So now the question is, how can we use our model in order to learn something new and in order to apply it to real-world examples? So first we look at GreenDroid, And GreenDroid is a set of functions on a mobile SoC in order to try to accelerate commonly used Android functions. And this is a great example for us to look at because there's multiple accelerators that can be invoked together in order to cover a large percentage of the overall code. And so we test our 4 different modes over both, if you implemented it in both a high performance core as well as a low performance core. And so with our analytical model, we can generate these heat maps where for a given design of either which of the 4 modes you're operating in, as well as the architecture on which you're operating, you can say, have a heat map which says at a certain invocation frequency, which is shown at the y-axis, where more frequently invoked is near the top, and for a certain percentage of code that's acceleratable, what is the estimated speed up that I can get for this accelerator of a given acceleration factor. And so if you now have a specific accelerator in mind, you can say basically in order, if it has a certain number of instructions that you're accelerating, in order to obtain a certain amount of percentage acceleratable, I'm going to need to invoke it at a certain frequency. So for any given one accelerator, you can plot a curve like this. And the points on this curve is kind of shown in the full out of order case, such as the blue bar, where as you follow this curve, the value of the heat map can be plotted on the y-axis to generate these sort of estimated speed up curves for the 4 different modes. So when we look at GreenDroid, on the top we have the high performance cores, and on the bottom we have low performance cores, and then we're sweeping in the 4 different modes for fully out of order on the left to fully sequential on the right. And so what we can see is that for the GreenDroid function, the curves that are in green, that there's a significant difference on the top from the leftmost to the rightmost curve, in that you can get high speed ups if you are in the full out of order mode, whereas you can actually get some slowdowns in the fully sequential. However, for the low performance core, there's less of a difference between the fully out of order and the fully sequential. And then the second thing that we note is we have now also plotted a more fine-grained accelerator, such as the heap accelerator. And as you have a more fine-grained accelerator, you have to invoke it more frequently to get the same percentage of acceleratable code. And so, especially in these cases, as you move, as it pushes closer to this top left of the curve, that you're starting to move into more of these slowdown regions. And so some of the takeaways that we have is that if you have a high-performance core, full out of order is more important. However, if you have a lower performance core, you may be able to relax some of the out of order execution, simplifying your hardware, and still be able to get some of the speedups that you are predicting. And then also, as you have a more fine-grained acceleration, it's more important to have more out of order execution, since you can start to push into these danger regions when you have fully sequential execution. And then some limits of the model is that we assume that there's independent accelerator and core instructions, and that the accelerator can begin execution immediately, and that the core maintains its IPC level. However, as a first level model, this is a great tool in order for designers to be able to get a good estimation of what will happen, and the ways that you can use our model in order to make informed decisions about TCA design. And lastly, our model is also able to show different things about how, like, the max speed up may not necessarily be when 100% of your code is acceleratable. So in this case, where you have a speed up factor of 2, that the full out of order mode actually receives its peak speed up of 3. This is because you're getting full concurrency when there's 2 times more work on the TCA as in the core, because the speed up factor is 2. And so this happens at 67% of code being acceleratable. However, when you're in some of these other modes, the point at which this peak occurs can be very different, and so this would be very difficult to design to just be able to intuitively calculate, but our model is able to pick up where these points are, and this helps determine the point of optimal balance for each of these different designs. So with that, I want to thank you for watching my video. If you have any questions, I'd be happy to address them in the 4th session on Wednesday. And if not, you're also welcome to email me. I appreciate your attention, and I look forward to hearing your questions on Wednesday. Thank you.